as you may know, lives and works in Los Angeles. He's on the staff of SCI-Arc, the only other totally independent school of architecture that I know of. David and Jan have been working together since 1979, and all the work of the gallery has been the product of joint effort, whatever the difficulties of the London-Los Angeles axis. The work on show, you will, I am sure, agree with me, is full of the optimism and faith in the future, which the application of present-day and discernible future technologies can provide. There is, too, the wit and the sheer skill, all of which reminds us nostalgically of that brief window in time here in London, when in the latter half of the 60s, a similar mood was discernible. David Nixon, an Inglesi abroad, and Jan Kaplicky, a Czech who has lived in Great Britain since the '68 events there, have both been touched by that moment in time, I am sure, as have others in the so-called high-tech camp. And in their partnership, they have obsessively carried that particular torch forward. Tonight, David Nixon will be talking about design for life in space, and will be looking into the foreseeable future, which for him is as far as the 22nd century. I'm sure that his lecture will in part be based on general US practical and experimental work, and partly on the NASA research projects based on SCI-Arc, which David and Jan have been involved with for some time now. I should also like to say that the Graham Foundation for the Advancement of the Arts in Chicago has kindly contributed towards the exhibition and catalog, and the exhibition will be seen in Chicago in the near future. David Nixon.
Thank you, Alvin. I had no idea so many people were interested in space. Or is it you're just trying to keep your feet dry? Anyway, in 1984, President Reagan commissioned a committee to draw up recommendations for the next 50 years in space. That is 50 years in space as far as the United States is concerned. And they came up with this government report, which is here, which is unlike any other government report I ever saw in my life. It's full of wonderful pictures, amazing ideas for the future. It's the kind of book you sometimes see in bookshops in the United States on glossy, exotic technology that comes out about 4 weeks before Christmas. And this book plots a series of moves which aim to take the United States from its current position with the Space Shuttle to the surface of Mars within the next 50 years. The report contains 12 key milestones, starting in 1993 with the initial operation of a permanent space station, followed by the initial operation of dramatically lower cost transport vehicles to and from low Earth orbit, addition of modular transfer vehicles capable of moving cargoes and people from low Earth orbit to any destination in the inner solar system, a spaceport in low Earth orbit, operation of an initial lunar outpost and pilot production of rocket propellant. That's the first move to the moon. Initial operation of a nuclear electric vehicle for high-energy missions to the outer planets. First shipment of shielding mass from the moon. That is mass which is required for solar and cosmic ray protection in space. Deployment of a spaceport in lunar orbit. Initial operation of an Earth-Mars transportation system. First flight of a cycling spaceship to open continuing passenger transport between Earth orbit and Mars. Human exploration and prospecting from astronaut outposts on Phobos and Deimos, which are the moons of Mars. And finally, ending up in approximately 2030, startup of the first Martian resource development base to provide oxygen, water, food construction materials, and rocket propellants. Now, the key thing to those 12 items is that 9 of them involve the presence of human life, either on board the spacecraft or directing it or in some way involved. And what I want to talk about tonight is basically how far we've come with the issue of designing for human life in space, starting with Skylab, the last Apollo mission of the 1970s, looking briefly at the Space Shuttle, Spacelab, Spacehab, which is going to be the first commercial venture into space as far as habitability is concerned, the space station, the lunar base, and the Mars mission. Can I have the lights off, please? Okay, off we go. Well, as far as the West is concerned, the first effort at coping with the problems of living in space was the Skylab, the 3 Skylab missions of the 1970s. The Skylab mission, the 3 Skylab missions and the Apollo-Soyuz mission were the last 2 groups of missions to run from the Apollo program. And the effort really with Skylab was to test human endurance in space. It hadn't really been done before. The maximum mission had been the Apollo trip to the moon, a trip lasting somewhere between 10 days and 2 weeks. There was very little known about the physiological, physical, and indeed psychological issues of living in space. As the Apollo program drew to a close, they decided that they would convert an upper stage of a Saturn V into a workshop living environment and send a series of crews up to test life in space. Basically, the Skylab unit consists of the docking port here down the bottom where the Apollo module came to dock, a long cylindrical workshop area, and down the bottom here a large trash tank to contain the vast amount of trash, the storage requirements for trash that built up during the periods, and as you can see a series of solar antennae and communications dishes up there. The 2 key living environments on Skylab was a workshop, which was approximately 7 meters diameter and about 4 meters high, and underneath that a living area. And these are a couple of shots. The shot on the left was taken from the Skylab trainer at the Johnson Space Center, and the shot on the right is actually looking inside Skylab from the workshop down to the living area. As you can see, the environment is very austere. There was no effort during the mission to cope with the issue of comfort. This was a mission basically using astronauts who had been trained for the Apollo program. They were used to the harshness of that environment. It was anticipated that there would be very little need to introduce any design with a capital D. But things got somewhat serious towards the end of the design program when various people were complaining that no windows had been provided in the shell because of the problem of introducing openings in a highly stressed pressure shell. Raymond Loewy, the industrial designer, was brought in and managed to persuade NASA to introduce a series of windows, and he was also instrumental in actually beginning to configure the sleeping compartment, some of the personal crew quarters, and indeed some of the furniture too, to try and give a quality of design over and above the harsh right-angle corner shiny metal approach which the program engineers had devised. There were 26,000 people working on this program in the 1970s. Now, this shot on the right is looking down, as I say, and you can see that there's a grid system, an ISO grid system, which was developed to do 2 things, really: to act as a space divider between the workshop area and the living quarters below, and also to provide a a standardized means of restraint and method of holding down any imaginable kind of object that piece of scientific equipment, whatever it happened to be, which would otherwise float around inside a weightless environment. Moving down to the level below, on the left is the wardroom table with above it the largest window on the Skylab spacecraft. And this was in fact, Raymond Loewy was absolutely right when he said that the one mitigating factor as far as human habitability was concerned in the space station would be a window, and that this would become a focal point for the entire mission. The debriefings that took place of the 9 astronauts, a total of 9 astronauts that flew on the 3 missions, clearly indicated that the top item of visual perceptual relief in Skylab was that one window, which they used to spend as much free time at as possible using. Each of the missions consisted of 3 crew members, and so the table was designed accordingly. And on the right is a slide looking into what they call a personal hygiene compartment, the bathroom, with the washing facilities and toilet storage facilities on the right-hand side. And I don't particularly propose tonight to go into the design of the toilet. That's a whole lecture in itself. Suffice it to say that the toilet design is probably one of the weakest points in the whole space program so far. And even the latest version on the Space Shuttle keeps blocking up. And somehow it seems extraordinary that they can design these amazingly sophisticated equipment to fly around the solar system and they can't produce a toilet. But anyway, that's the way it goes. So that gives you a feeling for the kind of quality of space that is inside. And both these shots were not taken with flash exposures. They were taken, I took them with a fairly long exposure, and what you see there is a slightly brighter level of the actual lighting that was used inside Skylab, a lighting which has very poor modeling qualities. Essentially it's shining in all the wrong places, and not being used at all to try and create any kind of visual interest. It was also a 24-hour lighting in the sense that it wasn't varied from day to night cycles, which is something that they're looking at now. Now, moving on to the Space Shuttle, and it's almost a year ago since the Challenger accident. I think one of the things about the press commentary on the Challenger accident is the fact that they have, to a greater extent, concentrated on the technological weak points of the design. And if you read through the Rogers inquiry, which was completed about 3 or 4 months ago on the accident, it's quite clear that that management errors were as much to blame as technological errors in the cause of that accident. Even to the point that had certain management decisions not been made in the management pyramid on the days preceding the flight, it would not have gone at that particular time under those particular temperatures and climatic conditions, and they'd have probably made it. That's how close it was. Anyway, accommodation on the shuttle is just as sparse as it is on Skylab, and in fact a lot more compact. Basically the accommodation consists of an upper flight deck where the pilot and the commander sit during ascent and landing, behind which here is the back of the upper flight deck with the windows that look out onto the cargo bay. There's a small hole in the step ladder down to the lower cabin, which contains most of the flight experiments which are used on board the shuttle, installed on board the shuttle, and indeed the actual crew sleeping quarters during the entire mission. The shuttle cannot stay up more than about 10 days because the fuel cells have a maximum life of that period. They have been talking about possibly building a deployable solar array so that they can extend the life of the space shuttle to something like 2 or 3 weeks. This is something that the defense people have been looking at, but so far has not gone into operation. Now, these are some shots inside the shuttle. On the left, that's the flight deck where the commander and the pilot sit. Blue fabric, about the only touch of color in the whole environment. As you can see, the rest of it looks very much like a fairly conventional flight deck in in Concorde or a 747. On the right, that is taken downstairs, directly underneath the seat on the left, directly underneath the flight deck, and the means of access is that hatchway at the top of the right-hand slide here, and a ladder, which is of course only used during before takeoff, when the crew actually install themselves in, and of course after landing. The rest of the time it's quite useless. One wonders why they didn't design a ladder to fold away, but there we are. And here is the hatchway into the tunnel, which leads to the Spacelab module, the pressurized Spacelab modules. Now, life aboard the shuttle is extremely, it's like an extremely crowded party. I was standing inside when I went to visit there with just 3 other people, and it felt extremely crowded. You could barely sort of turn around without bumping somebody, and as we all know, they've been sending missions of 7 or 8 people up. So one of the things they take great care in doing is crew selection. Crew selection and compatibility becomes terribly important, where you want to get people who get on with each other and don't start family arguments. On the right is the control panel and the windows, and actually behind these 2 on the left here. The 4 windows which are used for all the maneuvers, the visual maneuvers in space. The robot manipulator arm was built by Canada, is controlled from this panel here with this toggle handle, with the operator looking out of these windows. In space, in-orbit docking and visual closing on things like satellites is done through the top hatches here, the top windows. Now, moving on to Spacelab. Spacelab was the European contribution to the shuttle program, built by Air Italia, mostly with West Germany doing the fitting out, minimal British involvement. Spacelab was designed as a series of modular units of different length, connected to a tunnel to the lower accommodation, and it's essentially designed as a flying laboratory. The first time, really, that a conscious effort has been made to organize the experiments into a standardized rack format, which can be interchanged and modified during the course of the Spacelab missions, which were originally anticipated as flying about a couple every year. That's all changed now as a result of the Challenger accident. But the Spacelab concept has had a very profound influence on which I'll talk about a little later, on the direction that the habitability design is taking for the space station. And to my mind, it is a negative influence, because if you look at the Spacelab configuration, we go on to the next 2 slides, it is built very much with one gravity in mind. There is a floor, these are walls clearly, and there's a ceiling up here. Now there's a good reason for that, and that is that the cost of a typical space mission, 60% of that is vested in the testing and integration procedures that take place on the ground before it even leaves the launch pad. Those are extremely extensive and onerous, and of course this equipment is very heavy. The reason it's heavy is because it has to resist fairly high G-forces during launch, approximately 3G for the shuttle and about 1.5 coming back on re-entry. So these things are built solidly out of solid aluminum frames, and the equipment is very heavy inside. Well, that produced a follow-on need to devise a system of rail feeding these units in and out of the Spacelab as it lies inside the warehouse before it's finally assembled. And that essentially produced the need for a floor so the technicians could get in and out, and standardized wall panels so they could get access to installing the equipment. And the impact that has had is that the actual rack size, 42 inches, a little over a meter width, plus the actual configuration of flush fascia panels and a certain amount of angling up at the top, has influenced the design of the space station, which I'll come to a little later, in a fairly negative way by somehow destroying the ability to, the designer's ability to re-examine the architectural qualities of the space. In other words, the argument is that the technology follow-on must in fact sort of echo the technology that's already been tried and proven on the Spacelab missions. So that's one of the things that we're fighting against. The next key development in the Space Shuttle program is this object called Space Hab, as opposed to Spacelab. Now, Space Hab is a private commercial venture by a recently formed company in the United States, and it's like a little annex, if you like. It's designed to extend the accommodation inside the shuttle by providing facilities which can be used as extra sleeping space, extra meeting and working space, and also extra space to fly experiments during the lead-up to the space station program. That's very necessary because in order to attract industry to invest in the space station, it's necessary to have a capability to allow them to fly experiments beforehand so that they can test the microgravity, the zero gravity implications. And the space on the shuttle is incredibly booked up now as a result of the Challenger accident and also the reduced number of shuttle missions that were taking place before. There is a tremendous backlog of companies in Europe and the United States and Canada and indeed elsewhere who are not able to get their experiments on board a flight manifest until after the space station goes into orbit. So this design was an attempt to try and provide a plug-on annex facility, if you like, to enable industry to fly these experiments, roughly $1 million a box, to test out some of their ideas beforehand. But it's also going to be used for living in too. We've been looking at, with Space Hab, with ideas not for living in fact, but for storage, for actually configuring one of these as what they call in NASA language a fully dedicated storage facility, which essentially is turning it into a giant box room where you put all the non-essential equipment and supplies during the space station to make more room. But these two slides actually show two different versions of how it would be configured on the inside. And as you can see, we're still dealing with a situation where we have conventional floor and walls and roof and all the rest of it in a zero-gravity environment. The truncated top, incidentally, is required because the Space Hab sits directly behind the cabin portion of the shuttle, and it will fly. It occupies about 25% of the cargo bay, and it will fly with normal satellite deployment missions and a whole lot of other stuff. And it is necessary to have a decent line of sight from the upper flight deck, the control panel at the back of the upper flight deck, across the roof of the Space Hab to the back of the shuttle cargo bay, in order that the payload specialists, the people who actually launch the satellites and whatnot, can actually see the satellite leave the chamber. That's the reason for its rather odd shape. And the front to back dimension is incidentally about 3 meters. Now, the space station. NASA has this habit of producing these one-off gold-plated projects, and that's one of the things that the recent presidential committee are looking at, because they're saying that one of the problems with NASA over the years has been its preference for going for big multi-billion-dollar projects lasting 10 or more years. Apollo, the Apollo program, the shuttle program, and now the space station program. And essentially it's like it's the hourglass syndrome, where you have a series of bottlenecks one after the other, and not enough dissemination of scientific discovery and research into other fields. But there we are. Let's hope that this report is implemented. Just talk briefly about the space station. This was the idea which was under consideration at the beginning of 1984 when Reagan announced the program. And essentially it's like a big T, a giant T-shaped truss with the living modules down the bottom end, the nadir, facing towards the Earth for obvious reasons, because the shuttle is coming from a lower orbit up to dock. A series of sort of odds and ends of equipment, maintenance hangars for repairing satellites in orbit in various boxes hung down this long truss, photovoltaic panels on either side, and a lot of remote sensing, astronomy experiments, and communications antennae and various things up at the top here. Well, they were chewing this design around for a year or so and came up with a whole series of problems dealing with the preserving microgravity in this portion of the space station. As the shuttle comes into dock, it, as you might suppose, naturally imparts a force as it, however slowly it comes in. There's some force involved when it actually docks with the module, and that force creates a movement which disturbs any kind of microgravity experiment going on inside. And because this is rather like a big pendulum in a big grandfather clock, the thing will tend to start to oscillate backwards and forwards. Problem is compounded by the fact that there are only 4 struts that form the perimeter edge of this main beam here, and the oscillations that were beginning to occur were quite dramatic. And the whole thing, you know, the computer programs indicated the thing would start to wobble around quite a bit. So they changed the design to this, which is a much stiffer configuration with two main transverse beams, one here and one here, and 2 uprights here, with the modules clustered as close as possible to the center of gravity of the whole structure, so that if something came into dock, although there'd be a little bit of movement, it would tend to move about the center of mass, I should say, and that would reduce the problems with the experiments. Now, this project is undergoing a sort of catharsis at the moment, because what's happened is that the Europeans are objecting they're not getting a big enough slice of the cake. As a result of the fact they were severely shortchanged on the Spacelab program, they're playing hardball, as they say in the United States, this time round, and they're trying to get the most out of the project they can, quite rightly in my opinion. And now the famous Department of Defense has got its foot in the door and is saying, originally the US Department of Defense didn't want to have anything to do with the space station program because they thought it would draw funds away from their own space habitability research. But now the project is going ahead, they've turned around and said, well, maybe we can use this after all. And that is having major implications on the whole way that the thing is organized, as you can probably imagine, with security and all the rest of it. So this configuration is back on the drawing board. This was, as it was about 6 months ago, they had a series of living modules here organized in what they call a racetrack or figure-of-8 configuration, connected by nodes and small passageways. Obviously, solid architectural reasons for that. If you have a major emergency in one of these, you need an alternative means of escape. So that is provided by going out of one hatch one way or the other. And so linking everything together in that format is the most economical way of doing it. And here you can see little space hab units docked on the end there as stowage facilities, which is one of the things we're looking at right now. On the right is fiberglass, full-size fiberglass mock-up of one of the modules on the left, which they've been playing around with down at Johnson Space Center for a couple of years now. And their first effort at trying to get at the feeling for the inside was on the left, which I'm sure you'll all agree is looks a bit like something that PSA might have designed in the 1950s. It's a first effort to try and give a feeling for the wardroom. The wardroom, which I'll come back to later, is the key focal point on the space station in terms of habitability. It's the largest space. It has to accommodate up to 16 crew members when the shuttle missions overlap and you get a visit. And it really has to be comfortable. It's the only possible location on the space station where you can actually get some degree of spaciousness and comfort. Unfortunately, in the United States, they have safety people government safety people that come around and say, well, even though, folks, you're building a mock-up of what it looks like, you've got to put a floor in it, because what would happen if the congressmen and their wives came along and one of them fell over or something? So that's one of the problems that we all have in designing mock-ups, full-size mock-ups for space research, is the fact that they've got to be safe for people to walk through in high-heeled shoes and all the rest of it. And that's actually a very difficult thing to cope with. On the right, they have begun to cope with it by actually building a staircase and raised pathway all the way through one side. This design is a kind of follow-on to this version and was produced by an industrial designer in San Antonio called John Frasanito, who was a former associate of Raymond Loewy and therefore knows a lot about the space program. And his approach was quite different, because instead of taking the stowage equipment, the elements and the racks and all the rest of it, which tradition was saying that you should drape round the side, they grouped them all in a kind of wall configuration and attached them to a linear structural and utility beam here, which did leave you with half the interior of the cylinder free to try and humanize. I think that's the right word, humanize that. Unfortunately, this is not terribly efficient in terms of volumetric use inside the module, and this idea has recently been dropped. To my mind, it was a very good idea if it had been taken to a slightly more efficient level of volumetric utilization, because Frasanito was suggesting that all these units here are like giant crates, rectilinear in size, and they come up on consecutive shuttle missions and are interchanged. They contain all the necessary items for life support. And of course, as the supplies in one get used up, you simply exchange it for another one. It's a kind of containerization of the space station. Unfortunately, the rectilinear shape is not really very compatible with the shell, and there's a lot of wasted space behind. One of the things we're trying to avoid too. Now, apart from NASA, there have been the two key American aerospace companies who are competing for a big slice of this contract are Rockwell, who built the shuttle, and McDonnell Douglas, who built Skylab. So they picked the two people who've had previous experience in space habitability. This is this was on one of those strange days that you come across now and then in American companies, where they throw the whole works open to the workforce and their families, and they have a barbecue in the drive, and the place is crawling with security guards. And I managed to get in with a camera and take just one or two shots inside this. But this was, in fact, their first attempt to mock up the wardroom. As you can see, it's back to organizing the equipment and the racks around the side. All this is predicated on the fact that approximately 1/3 of the total available internal volume of any of these modules has to be taken by equipment and supplies. So essentially you're left with 2/3 of the space that people can actually move around in and float around in. So what they did was to group a series of these units to form what is effectively a rectilinear corridor running right down through the middle. And then these units are hinged at what they call these triangular blocks of space here are in fact triangular trusses which run down the whole length of each module and are attached to the shell. And these trusses are used as tie-back points for hinged tie-back points, I should add, for all these items of modular elements and equipment that form the lining. That's necessary because, of course, during launch with the 3G acceleration, these things transmit a lot of load to, have to transmit a lot of load to the shell, and they have come up with this as being the best way of doing it. Everything has to be hinged because the pressure shell has got to be fully accessible. There is a danger of micrometeoroid impact, tiny little particles which go straight through the skin and can cause leaks. Statistically, it happens. It's reckoned it will happen very rarely, but in that event, it's necessary to get these things away from the skin as quickly as possible and get behind with your bicycle tower repair kit or whatever to mend the hole as quickly as possible. The time it takes the air to get out is, of course, dependent on the size of the hole, and in certain situations, if it's determined that the rate of pressure drop is so high, they would just forget it and get out through either end and close the hatches, which is the reason for the dual exit. So this is actually Don McGargy, who's McDonnell Douglas's senior industrial designer, demonstrating to the crowd how it actually works. And that's a shot of the inside on the left. As you can see, they have attempted to open up the wardroom at this point by leaving a series of racks out here. You begin to get a feeling of the curvature, and you've got your two big windows. Opposite that, you've got the main table console, which is a linear element, so that you'd have people using it by essentially seating themselves, or rather restraining themselves side by side down each side. On the right is a further developed version on the left, which shows the next stage of design, if you like. The console in the middle has evolved to a partly demountable table here with a series of articulated surfaces which hinge out and close down when they're not in use. Lighting, you can see, is quite dreadful. I have to be careful what I say here, because I took this without a proper filter, and it's not actually quite that blue. It's not quite that austere, but as you can see, we're still talking about a rectilinear corridor. Some people refer to this as the men's locker room, and some people refer to it as the hospital corridor. That is right now the present state of thinking about how to make how to design the interior of the habitability module. Now, I want to move on and just talk a little bit about some of the design issues of living in space, some of the problems and the constraints. First one is its incredibly hostile environment, equally as hostile as underneath the ocean. That is to say, we cannot survive in it without some kinds of survival support. What kind of analogies do they use for trying to determine what it's going to be like to live in space for long periods of time? Well, a lot of psychologists and psychiatrists have done a lot of research on this subject, and they have done a series of analogy studies with similar situations down here on Earth, where the working and living environment is extremely severe, and where the impact of that environment on human performance becomes very critical. They have looked, of course, at the previous space missions like Skylab. They've looked at Sealab, Tektite 1 and 2, which are the United States underwater research projects. They've looked at submarines, extended submarine missions of up to about 80 days, Antarctic research stations, as you might suppose, particularly those with the 6-7 month winter over period when it's completely dark, and people at the station really cannot go beyond about 50 yards from the base, otherwise they get lost in the continuous blizzard. They've looked at oil fields, yacht racing, fishing vessels, so on and so forth. But one of the key analogies really is in underwater submarine missions. It's interesting to reflect that at any given moment there are 10,000 American servicemen on submarines, submarine duty, somewhere underneath the oceans. So, as you can imagine, there's a lot of research, studies, a lot of research material available on how these crews have responded and some of the psychological and physiological problems that have arisen. So that's one of the sources of information. The key problem on, as an aside, on extended submarine missions is the problem of depression, and not so much claustrophobia, because the crews are picked, very carefully picked, so that they pick people who they reckon will have minimum claustrophobia problems. But depression is the leading issue. The second constraint is the fact that the modules cannot be bigger than the shuttle cargo bay on the space station. That is probably the key constraint. The overall size of that is about 13.9, we'll say 14 meters long, by 4.2 meters diameter, giving you 177 cubic meters. Now, as I mentioned before, 2/3 of that is usable, so that figure comes down to 118 cubic meters. For a 6-person crew, that divides into 59 cubic meters of usable habitable volume per crew member for 90 days. 59 cubic meters is roughly the volume of an average British lounge, let's say, in a 3-bedroom house. For an 8-person crew, which is the crew size that they're looking at for, say, 2 years after initial operation, 1993, that figure comes down to 44 cubic meters, which is probably close to the size of your bedroom at home. So that gives you an idea of how much usable volume there is for each crew member for that 90-day mission. In addition to that, they do have their own private bedrooms, sleeping quarters, which are approximately 4¼ cubic meters in size. Now, another issue is the question of orientation. In weightlessness, you do lose, obviously, your natural references to the ground, to gravity. Your orientation, your visual cues, are entirely dependent on where you happen to be in relation to the environment around you. And the general feeling is that from the Skylab days, that could be a problem, particularly for some people. About 2/3 of the Skylab astronauts commented that they felt that some kind of conventional floor-ceiling reference is a good thing to have because it helps them find their way around the interior of the module. The other third said, forget it, it's completely unnecessary. We should start to forget it because now we're going into weightlessness. It's much more efficient and much more exciting if you can design the environment to be fully usable from whatever viewpoint you happen to have, or wherever your body happens to be. And if you look at some of the tapes of some of the life inside the space station, it's quite clear that those guys have a wonderful time sort of doing amazing sort of up and down routines and things. So it's questionable whether the present approach, which is being incorporated in the next brief from NASA of a floor and a ceiling reference, is the right way to go. Now, another very important point is scheduling and timelines. As you can probably imagine, time is money in space. It costs about somewhere between $40,000 and $50,000 an hour to put an astronaut into space on the shuttle and keep him there for 10 days and bring him back. And that's just the cost of what he does, his life support. That doesn't include the hardware. It's a lot of money, and so they're very concerned that the time is used as efficiently as possible. And these two charts, I won't spend long on them, but take, for example, two crews, two alternative 12-hour shifts, and looks at what those ships are doing every half an hour, and then you compare one to the other and see what happens at the changeover points, because that tends to tell you what kind of conflict you get on the interior design, particularly where you have two different crews trying to use the galley, the kitchen at the same point. One's cooking breakfast and the other's cooking dinner, which can produce problems. So you try and stagger that, and that's basically a juggling exercise to take the different activities, meals, training, exercise, sleep, personal hygiene, and put them into the kind of the kind of sequence which will cause minimal problems. And that's just a different version of the chart on the left, which looks at a sequential series of activities, and inside the habitability module, which is, I should say, that's the main accommodation module, and how that relates to other modules. That's quite important. We have to, every time you make a presentation, it's quite important to make that kind of reference, because otherwise some of the people who are involved in determining the timelines and the crew scheduling will not be on your side later on. They're generally useful people to have behind you. Now, coming on to the design of certain, designing for certain activities, workstations, key activity. The shot on the left is from Skylab, which shows Ed Gibson, who was one of the most vocal of the Skylab astronauts in saying what a lousy job the designers had done on the inside. And he came to talk to my students recently. And he's sitting here at one of the workstation consoles on Skylab. This is inside Spacelab. No attempt really to configure a workstation in that situation because of the limitations on the rack fascia, which I referred to earlier. But we have been doing some studies into ergonomics and what they call the man-machine, or rather the person-machine interface, the point of contact between the human body and the machine or item of equipment that he or she happens to be operating. And we've done a series of studies taking different types of activity and looking at how they relate anthropometrically to the actual workstation. So this one on the left, for example, is for planning and training. It's looking at the relationship between the two types of the full range of body size. I'll talk briefly about that. There is a NASA list of human body sizes, believe it or not, starting with something like a 6'6", 250-pound ex-American football player, going down to a 5-foot, sort of 90-pound female, because it's very important that all the equipment, as far as possible for the space station, is designed so that reach envelopes and the position of foot restraints, things that hold you in place, waist restraints, and all the rest of it, have sufficient degree of movement to be able to accommodate that range of people. In addition to that, you have the change in the anatomy, the change in the body geometry that happens in zero gravity. What tends to happen is that certain muscles cease to operate, and a lot of them tend to relax in zero gravity, and the body takes on a different proportion, which is dictated by the most comfortable point of rest. The nearest analogy is if you, those of you who like swimming and sort of floating around in swimming pools, will have done that in a situation where you're not actually moving anything. You're just floating on top of the pool, and if you've ever done that, you may have noticed that that your arms tend to come up and your legs tend to start to bend at the knees and spread out slightly. And some of those things are applicable in space too. The cone of vision changes, not only the actual angle, but the direction of the center of the cone of vision, which means that the relationship between your line of view and the fascia of the display screen becomes quite critical. And then you start to take those little studies and you put them together to see how they, in a fairly conventional architectural way, how they begin to intermesh with each other. Okay, now some of I have been running this project at SciArc for a couple of years now, and I had it under a extended NASA grant, and we've been doing some studies with some of the students there, of equipment. I've had about 10 students roughly over the past couple of years, and one of them built this. It's an attempt to take some of the ideas in the two previous slides and produce an adaptable workstation. This is all made out of foam board. I think they call it featherboard over here, and glue and bits of balsa wood and all the rest of it. And the idea here is that you have a series of panels which are hinged by means of a spring hinge which can be easily undone either with the left hand or with the right hand, so that the panel can be angled slightly to suit the maximum position of comfort. And this thing here, which looks rather like a large WC seat, actually is a simple mocking up of what would be a fairly elaborate padded waist restraint, which would essentially be a couple of sort of soft jaws which would come out from hinges at the back here and close around your waist as close as possible to your center of mass, which is your bottom of your tummy, which is about the most comfortable body position you can have, where you're held close to your center of gravity and you can spin around accordingly. One of the things to avoid is actually bolting people down into working positions, because much as, you know, the obvious thing might be to sort of put them in a kind of sort of medieval suit of armor, saying, right, you're not going to move, here you are for 3 hours. It's the easiest way the engineers can solve the problem. It would be quite intolerable, obviously, to do that. So the challenge is, and there's very little work going on in this field, to come up with slightly more comfortable and creative ways of doing that. And of course, we're presuming flat screen display technology will be with us on a regular basis 5 years from now. So everything we've been studying is dealing with maximum 50mm display screen depth. Okay, now we feel that here are a couple of analogies that we should be looking at when we design this kind of equipment. One is some of the advanced work going on in the motor industry. This happens to be the Ford probe, and they've done a tremendous amount of research on facial design, the use of different grades of foam, and of course the seating too, and trying to take that with that conventional computer equipment and mesh them together into something which is highly functional, combines all the equipment, but comfortable and responsive to the human body. And taking that idea further, looking at how on the right the human body has a very close relationship with machines. Typical of that is a motorbike, and on the left how some of the materials coming along, particularly for sports activities, are offering new horizons for new horizons for materials that you can use on equipment too. Now, four of the team actually built this model, which is like something, I suppose, a little bit out of a Star Trek thing. But the idea here was to take the ideas I've just described and try and put them together into a more amenable environment, particularly an environment that is respecting the curvature of the shell, because we feel from the studies we've done, the full-size studies we've done, that the living inside a curved shell could be a pleasant experience. And what you see here is actually a series of racks which are identical in width to the Spacelab ones I was talking about earlier, except they take some of our research studies, some of our research work, and look at how these racks can be theoretically configured to respond to the interface with the human body. We've been using, we call her Lucy, this dummy on the left here, to help us in those studies. And of course lighting, one of the things that came up very early on in the project was that integral lighting is terribly important much in the same way that lighting, you know, a good theatre designer or a good movie set designer will rely heavily on lighting to change the nature of the space and the quality of it. We think that the same kind of approach should be adopted inside the space station. And moving on, wardroom table, eating in space can be a very difficult experience. There's a little interesting thing here. You see all this food floating out of this cabinet. That's popularly referred to as the jack-in-the-box syndrome. And essentially that happens every time you open a compartment in space where the stuff inside is not held down. Everything inside is actually bouncing around inside the box. And the minute you open one side of the box, it sort of goes whoosh like that. And you have to sort of, apparently they spend a lot of time just simply grabbing these items as they come out of the box and trying to stuff them back in again. So that's John Young on the right there, who's, I think, the senior US astronaut at this time. And another more views on the Space Shuttle. They don't even have a table. They have to get the food tray and just sit down wherever they can find space. And here's a shot of an astronaut just sitting on the floor behind the console on the upper flight deck having dinner or whatever. The latest version of the table from McDonnell Douglas's industrial design department there. Now our table, which we've been working on, is just about to start prototype development at NASA Ames in California, and if all goes well, we hope to be flight testing this in about a year's time on one of NASA's reduced gravity flights, which essentially is a stripped out 707 that does a sort of series of roller coaster loops at 35,000 feet, and you get something like 40 seconds of weightlessness. I'm sure you've probably seen shots on television of people bouncing around inside foam padded aircraft, and that's essentially what we're hoping to do with this. I have a student who's going on one of those flights in about 2 weeks' time with something that he's designed. It's a wearable workstation. The idea of this is to say, well, let's bring something at least with which we're familiar from Earth, like a symmetrical dining room table. If we're dealing with an environment where all the corridors are linear, series of linear routes through the space station, it would be nice actually to have something sitting in the middle of that route which changes the space. So we're trying to promote the idea of a symmetrical conventional dining room table suitable for 4 or 8 crew members. This was the first attempt at the mock-up. Again, we made this out of foam board, feather board, and little bits of whatever we could find to give the feeling of it. All this work was done full size, and onto sleeping compartments. This slide, which I'm sure everybody's familiar with, is actually approximately the same size as the private sleeping compartment that NASA have allocated for the individual crew members. Very early on it was felt that somewhere on board each crew member must have a very private personal space. All part of the psychologist's study into human behavior and territoriality in extreme conditions and all the rest of it. Everybody has got to get away from everybody else. And this looks at, as you can see, the bed it's not really a bed. It's like a sort of day bed, I suppose, profiled to the zero gravity shape. It's extremely tight, and you can just sort of crawl in there, and then you have a workstation or something in front of you and a television above, and a series of storage compartments on the wall. That was NASA's first attempt to mock up a workstation. Now, our studies, we've been looking at that too, and we're suggesting a slightly different approach where you treat the sleeping compartments rather like a turbine. There are going to be situations, for example, where married crew members go up, and there are going to be situations where on specially long missions, crew members may demand extra space. So instead of a series of rigidly defined walls and compartments, we're suggesting a series of sliding partitions. So the things can be slid back like a sort of rotating pack of cards, if you like, to give increased facilities as is required. and then an attempt to fit out those facilities as comfortably as possible. An attempt to try and, on the right-hand side, to break down those comfort features into sort of manageable components which the engineers can understand. It's one of the problems you're all familiar with as architects, is talking to engineers in their own language. Now, storage, finally. The conventional ideas about storage are looking something like the food storage kitchen on a 747. Very little effort has been made to treat storage as a major design item, yet it is, because it's occupying so much valuable space. And we are looking at different things. Before I go on to that, the slide on the left is the aerospace industry's idea of a storage compartment. And this is, again, one of my students who was looking at the idea of modular storage units sliding up and down a structural and utility distribution beam running along the module like that. What I like particularly about these two slides is that this one was done by a company operating on a multi-million-dollar government contract, and this one was done by 4 architectural students over the space of 3 months, basically working for free pizzas. So. Okay, now storage briefly, we're suggesting let's look at what do we have down here that works. Shoe bags, which we're all familiar with, hanging on the wall. They can be decorative, nice colors, and they work much better than those tin boxes because they actually retain things and they don't float out when you get them. Also, if you can imagine this as a personalized giant thing, about 3 times the size as it is on the screen, in that you can put the whole 90-day supply of crew clothing and personal effects, and we're suggesting that that is rolled up and goes up with each crew member like sort of a personalized sleeping bag, and when he gets into space he unrolls it and puts it on the wall, and it forms his storage wall, soft storage wall, and storage wall with his own personal selection of colors or material or whatever you want. On the right, the possibility of introducing graphic panels onto these storage wall elements, either on a permanent basis or rather like a sort of postcard grid, if you like, on a basis whereby you can put them on one day and take them off the next according to your mood at the time. Now, nature. First slide of some plants we've seen. There's a big controversy at the moment as to whether the shuttle will go up with something growing in it. Again, the engineers are saying it's a big problem to have plants in space, but we all know they've got to have plants in space because the space station is the first of these whole series of long duration missions talked about earlier to the Moon and Mars and all the rest of it. And there's absolutely no way that those people are going to survive on packaged sealed food during that time. So some people are looking at the idea of what we call ambient plant containers, where there are certain types of plant which can survive inside the environment, the ambient air environment inside the space station. And there are certain ones which may be doing double duty as a botanical experiment, which would be accessible by climate-controlled glove box compartments. So again, this is some full-sized studies we've been doing at SciArc on that. Now, I don't want to go on too long, but just jumping ahead now to the Moon, the report I was talking about earlier is looking at the year 2005 for a permanent lunar base. It's part of a much more extensive infrastructure which NASA are looking at, a whole series of way stations for flights that are going to do all sorts of things in near space during the next century. Spaceports orbiting around the Moon, the space station, and space station also at the Lagrange points, which are the points between the Earth and the Moon where the orbit is completely, the position is completely stable, not affected by gravity of one body or the other. Back on the Moon, Now, the conventional wisdom is to bury the lunar base underneath the lunar soil. The reason for that primarily is the danger of solar flare radiation. Solar flare radiation is the biggest space hazard to humans. Solar activity, sunspot activity, which occurs now and then, produces very, very lethal doses of radiation, which, if exposed to, can cause death in about 5 hours. So you've got to get, if that happens, you have to have protection from it. And 2 meters of lunar soil is generally considered to be the minimum protection necessary for that. So the general idea has been to bury the initial lunar base underneath that soil. And we've been suggesting that that's not a terribly good idea, because if you have a need for emergency access to the outside of the shell, or you need, for example, to reroute your utility environmental control life support systems, as they say, to and from one module to the other, you're not going to be able to get at the outside. So it's much better to produce some kind of simple superstructure with a mesh, a very finely woven mesh, so that you can dump your 2 meters of lunar regolith directly over the top and still have access, also pull-in, pull-out access for the modules underneath. And we're busy sort of promoting that over at the moment. There's not a great deal of interest in the lunar base per se, because everybody has got their eyes firmly directed towards the space station, but the general feeling is about a couple of years from now the space community is going to get back and say, well, what are we going to do about the lunar base? And that's when we're hoping to be able to help them. So, all right, and finally, Mars, and perhaps the most exciting thing that is happening now is the possibility of a joint US-Soviet mission to Mars just before the turn of the century, which is being raised at the highest levels between Russia and the United States at this time, spearheaded by an ex-Apollo astronaut and scientist by the name of Brian O'Leary, who has dedicated his life to trying to achieve it. And Brian has done a number of studies, and it turns out that the conjunction, the relationship between the Earth and the Mars in 1998 is perfect for an outbound mission via Venus. It may sound odd because Venus is inside the orbit of the Earth, but if you can imagine it crossing the plane of the solar system, it would naturally go inbound before it goes out to the other side of the circle. It's all to do with planetary mechanics, which I know absolutely nothing about. But essentially, there's a very favorable launch window in 1998 for that. The round trip would be a little under 2 years, and the idea behind the scheme is that they will come back about a month before the change of the millennium, and so there'll be a big party somewhere and all the rest of it. And even suggesting that that will be the date of international nuclear disarmament. That's being promoted too. So this is looking at that very briefly. They wouldn't land on Mars initially. They'd land on one of the 2 satellites of Mars, Phobos or Deimos, which are large lumps of rock 2 or 3 miles across, with no gravity, which means that they can come in and actually tether the spacecraft. They'd actually physically have to tether the spacecraft to the surface with cables. But the beauty of it is that coming in and out of that landing to the satellites requires very little, how shall I put it, very little effort in terms of burning fuel, which is the big problem in these kind of missions, is to reduce the amount of fuel you actually need to take with you. And that, very briefly, raises the issue of artificial gravity, because up until now, with these relatively short missions, it's been pretty well acceptable for astronauts, crew members, to survive in a weightless situation with approximately 1 hour's exercise a day. There is no information available at the moment on the really long-term effects of what it would be like on a 2-year mission, whether the physiological changes would be beyond the point of reversal to a normal Earth environment on the way back. And the Russians are not giving out much information on whether their salute, their longer salute missions, what the effects have been on the astronauts there. So there's some concern about that, and there is an attempt to try and determine what would be an acceptable level of artificial gravity on board this mission. And Brian O'Leary, these two sketches are sort of right at the cutting edge of thinking on this this vehicle that would take the mission to Mars, where you have the main external tank at the back with an enormous fuel, and a series of different modules and payloads stacked salami fashion, one in front of the other, in order that they deploy and extend out in an organized fashion. Now, what happens is that once the spacecraft has left Earth orbit, the habitability, the living modules, will extend outwards on tethers about 200 meters from the main spine here, and the whole assembly will begin to rotate at approximately 1 revolution a minute, and that will give you, at a sort of 200 meters out from the center, about 1/2 Earth's gravity, which means that essentially during the 9 or 10 months of the mission from Earth to Mars, you are maintaining some semblance of gravity. And the big question now is whether, it's kind of an argument that's going on as to whether the increased cost of that is worth it in the view, or from the point of view of the fact that maybe there are other ways to reduce the problem of weightlessness, the problem of physiological degradation. For example, choosing certain types of astronaut who don't require a lot of exercise and will not suffer some of the problems. And that's it. Thank you. Thanks, Howard.
I don't know that there's anyone here who has the courage to ask some well-founded questions. Cedric Price.
Well, there's one thing, there was a point you made about being a zone between Earth and Moon, where there would be a balance in relation to gravity. Well, that throws me a little bit, because I don't quite understand how the tides work then, unless it is a very sort of bent orbital zone. But the main question was actually largely answered by your point about artificial gravity. But surely, if that is being looked into, which it is not only by O'Leary, but by the Russians, then I don't understand some of your earlier, or perhaps you make it a bit clearer, some of your earlier points in talking about the tubular section. And there was an implication that you, and I may have got it wrong, rather preferred something which showed the curvilinear nature to the limitations, rather than the squared off bit that Westinghouse or McDonald or whoever had done. Which is rather like the business of Queen Victoria and the reversal of attitudes to square railway carriages. Now, funny enough, people now don't like the curve in Concorde and prefer the flat bits in the wide bodies, 747. But then you go back to saying, having accepted that there's a linear progression, you're now looking at the dining table down the middle of the room. And I can't quite see, in relation to your acceptance that there is weightlessness, because it's only at the end you talk about artificial gravity, which primarily most of us know about lead boots for divers, But I mean, that sort of investigation, isn't that more likely to be a fruitful investigation that will result in your various designs of the sleeping bit or tables and things, rather than this business of, there was a certain sort of formalist quaintness about, well, we're living in something and it is a tube and we should get used to this. So those are the three questions, really. The first one was just, I didn't know there was a zone between the moon and Earth, where there's no gravity pulling either way.
Right, I'm probably the worst possible person to explain that, but there is a series of actual zones where the gravitational pull of the Earth and the Moon balance each other out, so that if you position a an object at that point, it will tend to stay there. In all other situations, it begins to move one direction or the other. Right. I think your point is well made about the, how can I answer it? The space station, there was never any possibility of artificial gravity on the space station because they simply didn't know how to cope with it when they were designing it, and they don't really now. And the feeling always has been that there are other ways to get around the problem, and they're only up there for 90 days anyway. Our preference for the curved approach, I think, is based on a sort of, I suppose, one's architectural background, which leads one to believe that if you have something that that is geometrically rather nice, it might be nice to try and play that up, rather than spoil it. And one of the problems with the rectilinear approach is that you lose valuable space at the back of those units. You get this little slice. We have all felt that the more space you can conserve in the middle, the better, and the way really to do that is to try and keep those curves going down. The problem we're having is that those curves are incompatible, as you can imagine, with the equipment geometry, which is box-like.
You'd have Lucy go all the way around.
Yeah.
I mean, she could actually, in your slide, been...
Yes, she could. Yes. Yeah. Now, Lucy...
Rather than that funny T-shaped section that
Right.
you're talking about,
Right.
down the middle of the tables or whatever they were.
Right. Yeah.
Which was a top and bottom
Yeah.
directionality.
We did 3 studies, and Lucy was the third and the most I suppose, daring, if you like, and the one we found the most satisfying, and would be the one we would love to carry on to the next stage. Unfortunately, they're not letting us do it. We have to go back to not quite that, but something fairly close to it. Any more questions, anybody? Okay.